Hello and welcome back. Alright, this is our last video on the topic of sorting, at least until we maybe delve into some other data structures. In this one, we're going to be focusing on Quicksort. Now, as the name implies, this should be a quick sorting algorithm. And in practice, we find that the performance of Quicksort is actually n log n. However, there's a caveat I just want you to be aware of, that the performance of Quicksort under the precise wrong conditions can run n squared. But that's typically never the case. Actually, 99% or so. Some high probability that you'll never get into that case. So for the most part, Quicksort is actually running n log n. Perfect. Quicksort is also able to sort in place, so it doesn't require any additional memory like our merge sort algorithm did. We've looked at 5 different sorting algorithms, and you might ask the question, hey, why don't we just use a single sorting algorithm all the time? Well, that would be great if we always had the exact same conditions that we wanted to sort data around, but that's seldom the case. If we had, uh, 10 billion records that we needed to sort through, Quicksort's actually not going to be the best sorting algorithm that we want to use, because in order for Quicksort to work efficiently, everything needs to be stored in memory already. Well, you're probably not going to be storing 10 billion items in memory. So a sorting algorithm like merge sort is actually going to be better for you, because merge sort can be written in such a way that it can pull in data in chunks at a time. So Quicksort is really great for in-place memory sorting, or in-place sorting. Uses no additional memory, but everything already has to be stored in memory. Merge sort is going to be great for if you have to sort a bunch of data that's on a disk or on some slow reading access. Merge sort is going to be a good option for you there. And there's actually specialized versions of each one of merge sort for different kind of file structures and things like that. But just in general, that's why we choose different algorithms. So you need to look at your situation, and you need to apply the right algorithms for your situation. Otherwise, you're just kind of doing yourself a disservice, and you're going to have problems down the road. Okay, with that long mouthful, let's go ahead and take a look at what Quicksort, what the strategy behind Quicksort is. Okay, let's draw our standard little array box. Okay, so I'm just going to leave it empty. Just pretend there's some random values inside this array. Now, the idea behind Quicksort is that you have a pivot value. And the idea is that you're going to collect all of the items within the array that are less than the pivot value over on the left side of the array, and all of the pivot values that are all of the values that are greater than the pivot value on the right side of the array. So at the end of your first pass, what you're going to have is you're going to have this pivot value p in the middle, and you're going to have all the values that are less than p over on the left, and all the values that are greater than or equal to p on the right. So let's go ahead and walk through this algorithm, and then we'll kind of get a better idea of how we want to actually write the code for it. All right, so let's start off with a small array, and we'll have the values 2, 1, 4, and 3 in here. Okay, and so now we need to choose a pivot value. Well, the interesting thing about Quicksort is that you can choose any pivot value, or you can choose the pivot value however you want to. The only qualification is that the pivot value must be a value within the range of the array. That is, we need a pivot value so that we can actually create this relationship. So I'm just going to arbitrarily pick the first item. You could pick the middle one, you could pick the last one, you could pick the second one, you can do whatever you want. But you just need to pick it and then use it throughout the rest of this portion of the algorithm. Okay, so my pivot is going to be 2. Okay, and so Now the strategy that I'm going to go through here is that I'm going to have two counters. I'm going to call one S for the starting point of the array and one E for the ending point of the array. I would use left and right, L and R, but L is kind of confusing between 1 and also I, so S and E will be good. Okay, and so now the idea is we want to move S up the array as long as the value at the index of S is less than the pivot. Then we want to pull E down the array while the value in the array is greater than the pivot. We want to do that because, well, if it's less than the pivot, we know that it's going to go ahead and stay on the left side. If it's greater than the pivot, we know it's going to go ahead and stay on the right side. So after we move S and E up and down the array, then we're going to swap those values as long as S is still less than E. So let's go ahead and walk through this example. All right, so we're going to ask the question, is 2 less than P? No, it's not. All right, so we know 2 is a candidate to get swapped out. Okay, so now we're going to go ask the question for E. Is 3 greater than 2? Yes, it is. Okay, so we don't need to swap E. So then we ask, is 4 less than, or is 4 greater than 2? Yes, it is. Perfect. Okay, so now is 1 greater than 2? No, it is not. All right, so what we need to do is now check. Hey, is S less than E? It's important to do this check because if these two cross, if S and E cross boundaries here, then we know that we're actually done looking through the array because now we're looking on the left side of the pivot for greater than values, and that's not what we want. And we're on the right side of the pivot for less than values. But we've already established that the right side is greater and the left side is less. Okay, so this is our first interesting point in the array, or in our algorithm, where we actually need to swap the 1 and the 2 values. So we have 1, 2, 4, and 3. Okay, and so S is pointing here, and E is pointing here. All right, so it looks like we're done in the array, and with this example, we kind of are, but our algorithm, we need to continue doing this until we actually do cross paths with the S and E to ensure that we've actually collected all of the values that are less than the pivot on the left side and all of the values that are greater than the pivot on the right side. Okay, so we ask the same question. Is 1 less than P? Yes it is. So I know that that's actually a value that we want to keep there. So we're going to move S to point to the second value in our array. All right, so now we ask the question, is 2 greater than P? Well, no, it's not. So we are actually going to stop there. Okay, so now we have to ask the question, hey, is S less than E? No, it's not. So we don't need to swap any values at this point. And now S is not less than E anymore, so our outer loop we can stop. Basically, they've hit paths, and so we know that there's no point in continue on checking down the right side of this array, and we know there's no point to check the left side of the array. We've already met the conditions that we were trying to solve up here. Now the interesting thing here is that if they actually do equal another, we're going to need to actually say, hey, we want to point S to here. And the reason for that is Quicksort is going to be recursive. So what we need to do is we need to continue sorting this guy, and we need to continue sorting this guy. So with that, let's go ahead and jump over into Xcode, and hopefully this will become a little bit more clear. And we'll jump over to the whiteboard if we need to as well. Oops. Okay. So this is just a new C++ empty project. So let's go ahead and define what our quicksort function prototype is going to look like. I'm going to call it Qsort. and it's going to need to take in an array of items, and it's going to need to take in a start point in our array, and it's going to need to take in an ending point of our array. All right, so far so good. We've already seen this before. So now we have the qualification of if our starting point, so we're doing recursion. So we need some sort of base case so that we don't end up in an infinite recursion call. And that base case that we're going to be using for the implementation of our quicksort is when that array size is 1. So essentially, that's when start and the endpoint both point to the same index value in our array. When we hit that point, we're done, and we don't need to actually do any more of the algorithm. So if start equals end, go ahead and return. Now we could do this check later on to stop us from calling the quicksort algorithm or function again. You can do it however you want to. I'm just going to do it there. It's a little bit easier for this purpose. Okay, so now we need to create our S and our E counters. So S is going to equal start off at the starting point, and E is going to start off at the ending point. And remember I said that I was going to pick my pivot point by just using the first item in the array. And so that's whatever S is pointing to. Okay, so now we know we need to write that loop while S is less than E. So essentially, until we cross paths, we need to do some work. So just use a while loop while S is less than E. All right, now we know we need to move the S pointer, or the S index value, up the array while we have some value that's less than the pivot. So I'm just going to create a simple little for loop to do that for us. So while S is less than the pivot, go ahead and increment S. Be sure to put this semicolon at the end of your for loop. Okay, and so now we're going to do the E check. And that E check is while the items at the E location, or the items at the E, the value in our array at the E index is greater than the pivot, then we decrement our E counter. We need to pull that pointer down the array. Okay, and so now now we've moved our S and our E values, and so now if we have any overlap, let's jump over to our whiteboard again. So if S is less than E, like this case right here, then we know we need to do our flip. So let's go ahead and write that. So if S is less than E, go ahead and swap values. So we're going to need a temp and just items S. Items S is items E. Items E equals the temp variable. And then, since we swapped them, we know that we just need to go ahead and move those values along for S and E, because we know that when we move things, we know that the conditions are correct, where the left side of the array is going to have a value that is less than the pivot, and the right side of the array is going to have a value that is greater than the pivot. So we don't need to check that again. And really, that's all the work that we're going to end up doing. And so outside of our while loop, when they overlap, there's two possibilities. One, S is actually going to be less than E. S is actually going to be greater than E. The other possibility is that S equals E, and in that case, we actually want to increment our S variable. So let's go ahead and do that. If S equals E, then move the S pointer up. And so the reason we want to do that is when you end up with a value that actually matches, you'll end up with an infinite recursion, as you'll always be passing in the same values in the array. Okay, so now remember, Quicksort is going to be using recursion, so we do Quicksort, or call Qsort. Items, we need to sort the left half of the array first, so that's where our starting point was, and it goes until wherever our E value is at. And then we need to sort the right half of the array, and that's going to start from our S point and go to whatever our ending value of the array that we passed in. And that's it. That's Quicksort. So let's go ahead and test out a few times and make sure I didn't mess up anything. Okay, so let's create an integer array called items, and we'll just initialize it to 3, 2, 5, 9. That's good. And we'll go ahead and create our little helper variable to get the length. And I'm going to go ahead and create a helper function to print out our array. And pass in a little message. Unsorted items length. And then we'll call quicksort. And we'll pass in items, and we'll pass in 0, and we'll pass in length -1. And then we want to print array again, and then we'll print out the sorted array this time, which is items and the length. Okay. So I'll just create a new function called print array. It's going to take a constant char pointer msg, short for message, and then it's going to take in the int items array, and then the length. Sure, we'll make it a constant int. Okay. Now we'll make this constant too, just for fun. Okay. So now what we want to do is go ahead and print out first our message. So standard cout message. Give it a nice little end line here. Then I'm going to print out each of the items. So I'm doing length -1 because I'm gonna do it fancier this time and not print the comma at the last spot. So we have items I, and then we'll do standard cout items length -1, standard and 9. All right, so we build this, good, no errors, and if we go ahead and run this, you'll see that we have 3, 2, 5, 9, which is indeed our unsorted array, and our sorted array is 2, 3, 5, 9. Perfect. So we can come in here and we can add a few values. I'll even add some duplicates. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8. 8. Go ahead and build it and run it. And what do you know? All 8 of our values got sorted correctly, even with our duplicate values. So that is Quicksort. And if you look online, you'll see a bunch of different implementations of Quicksort. It's really actually fairly straightforward to write. It uses recursion, so be sure you understand that. But with that, I think that's going to wrap up our sorting week on sorting. And next week we will start taking a look at some data structures. I think we'll be doing trees. So with that, thanks.